Hello students, and welcome to the next class on computational chemistry. We are still dealing with the introduction so that we can provide you a strong framework of what is computational chemistry and what we are going to deal in this course. So the outline of today's presentation will be the introduction and the methods that are used in computational chemistry, such as ab initio, semi-empirical, density functional theory, and the new developments such as quantum mechanical, molecular mechanics theory. So first of all, what is chemistry? We all know that everything from microscopic to nanotechnology to daily life, environmental and biological, everything has chemistry in it. Okay, chemistry plays a big role in all of these fields. Again, what is computational chemistry? Now, computational chemistry deals with from small molecules to large proteins, DNAs, even crystals and surfaces. From species in vacuum to those in solvent at room temperature and under extreme conditions of the high temperature and pressure, for example in the sun. Right? Then from structures to properties to spectra, be it UV, IR, Raman, NMR, VCD, to dynamics and even reactivity. Also, all experiments that can be done in lab and all those experiments that cannot be done in lab because they are too big. So when we are dealing with computational chemistry, do not forget to think big. Again, the central theme of computational chemistry. We have heard about the central dogma of molecular biology, in which we first do the sequencing to determine the structure. From the structure, we carry out the dynamics, and the dynamics finally gives us the functions, and the function is further evaluated. Similarly, for computational chemistry, first we take the structure, then we perform the dynamics, and finally determine the reactivity of that system. This is the central theme of computational chemistry. Now, what is computational chemistry? Computational chemistry is the application of computational methods and algorithms in chemistry. For example, when we say quantum mechanics or QM, then we have to say that it uses Schrodinger's equation, right? Schrodinger's equation, which is H psi equal to E psi. It is also known as quantum chemistry. But computational chemistry is not just limited to the use of Schrödinger equation. When computational chemistry is used for molecular mechanics, then we use Newton's law F equal to ma. Even Newton's law is applicable when we do molecular mechanics using computational chemistry. Again, there is another technique of using empirical or statistical mechanics. For example, quantitative structure application relationship, QSAR, which is widely used in clinical and medicinal chemistry. Now let us look at how big systems we can deal with. For example, with ab initio method, the number of atoms is limited because ab initio method cannot be used for systems with more than 100 atoms. Assuming that we have a typical computer setup, that is the number of CPUs, memory, disk space, etc. is the typical that we use, then we say that we find that for ab initio method it cannot be used for more than 100 atoms. DFT is limited for 1000 atoms. Semi-empirical method, in semi-empirical method we can study up to 10,000 atoms, and for molecular mechanics, molecular dynamics, we use even above lakhs of atoms. Again, when we see the starting point is the time-independent Schrödinger equation. We know that Schrödinger equation is H psi equal to E psi, where this H is the Hamiltonian, psi is the wave function, E is the energy, and again this is the wave function, right? So this is the form of time-independent Schrödinger equation. Hamiltonian, we will look into it in a little bit, is represented by this equation, right? Now let us see what it is all about. So to solve the ab initio theory, to solve equations in ab initio theory, we have to know the variables, the 3 n spatial variables. N is the number of electron And what do we approximate? We approximate this variationally, variation theory, and perturbationally, this energy value. We determine using variation theory that you will learn while studying quantum chemistry and perturbation theory. Okay. Let's see what is the Hamiltonian of a molecule. When we say Hamiltonian of H psi equal to E psi, this Hamiltonian actually represents all the interaction that is possible in a molecule. The kinetic energy of electron is there, the kinetic energy of nucleus is there, there is electrostatic interaction between electron and nucleus, there is electrostatic interaction between the electrons and electrostatic interaction between the nuclei. For example, if we take a one nuclear system, one electron system, say hydrogen ion, then we'll have to find out how many nuclei is there, how many electrons are there, and with that we can determine the form of Hamiltonian using this equation. Okay, don't worry about this form of Hamiltonian. Each term can be determined if we look at specific molecule. Okay, so do not be scared of it. We will solve the Hamiltonian of small molecules one by one. So what is ab initio methods? Ab initio methods gives the accurate treatment of electronic distribution using full Schrodinger equation. Okay, it can be systematically improved. Why it has to be improved? So that we can obtain accuracy. Okay, also ab initio methods does not need to be parameterized. That means it does not need external or internal parameters. Okay, no parameters are needed or calibrated with respect to the experiment, but it can describe the structure, properties, energetics, and reactivity. Now what do the words ab initio actually mean? Ab initio means from first principles. Please remember this, that what is ab initio? Ab initio means from first principles. Okay, and it was invented by Bob Parr in 1950s. So this is the reference of the original paper in which it was published. You can pause the video and look it up for your convenience. Okay, so International Journal of Quantum Chemistry in 1990 it was published. Again, let us look at the three most important approximation that forms the very basis of solving the equation. First is the Born-Oppenheimer approximation. What is Born-Oppenheimer approximation? Some of you may know that Born-Oppenheimer approximation states that electrons act separately from the nucleus. That means electron and nuclear coordinates are independent of each other. That is, electrons and nucleus are independent of each other. Why we are making this assumption or this approximation? So that we can simplify the Schrodinger equation in solving it. Okay. Second approximation is the independent particle approximation. It states that electrons experience what? Electron experience the field of all other electrons as a group. Okay, not individually. Suppose there are 3 electrons, then each of these electrons, say the first electron is experiencing the other 2 electrons as a group. As a group it is affecting the first electron and not individually. And this is very important because it gives rise to the concept of orbital, be it atomic orbital AO or molecular orbital MO. The third approximation is the LCAO or linear combination of atomic orbital molecular orbital approximation, in which it states that molecular orbitals can be constructed as linear combination of atomic orbitals to form Slater determinants. Here we have elaborated the Born-Oppenheimer approximation in details, because the Born-Oppenheimer approximation says that the nuclear and electronic coordinates are independent of each other, because nucleus is heavier than the electrons and the electrons move much faster than the movement of the nucleus, correct? Now, if we say that the nucleus does not move or the nuclear position does not change, then the nuclear energy, kinetic energy, becomes 0. and the Hamiltonian that remains depends only on the kinetic energy of electrons, and such a Hamiltonian is known as electronic Hamiltonian, and this is the form of the electronic Hamiltonian. If you compare it with this, we find that here this term, one of the terms is not there, right? So this is there. How many terms we have? 1, 2, 3, 4, correct? In here we see 1, 2, 3, 4, 5. So one of the terms, this term, was eliminated. Okay, then we calculate the electronic wave function and energy. So once we have determined the Hamiltonian, the calculation of electronic wave function is done and energy is calculated, and we find that the energy depends on nuclear positions through nuclear electron attraction and nuclear repulsion. And when the particles are at infinite separation, this value of E becomes equal to 0. Okay, so we will continue the same discussion in the next class, okay, that I think will be held in offline mode. So I'll see you in the next one. Thank you.